This talk has a kind of a funny genesis. It came out of a talk I developed for Signal Processing Society a few years ago, and but I'm going to blend in a little comms examples here, so we're all so we'll all be involved, I guess. If you went to Mars a few years ago, and then you came back and you looked at signal processing and communications prior to when you left and to when you came back, you would say, my goodness, there's a remarkable change, huge change. And that's been brought about because of deep learning and all the different offshoots of it. And so the goal of this talk is to kind of ask ourselves, so what's really new in signal processing specifically with deep learning? What has happened that is so tremendously remarkable? What are the fundamental things that I'd like to understand about the new tools that we've got? And I'm trying to be as agnostic as I can be. I have my own opinions, of course, but I'm trying to make this as level-headed as I can. So you're all familiar with the AI and machine learning landscape, in this large body of what we're kind of generically calling artificial intelligence. There is machine learning, and inside of that, deep learning. Of course, the diagram isn't really to scale because deep learning is really kind of dominating the world to a large extent. And it's worth reminding ourselves a few things about it. Machine learning is really a big field. And this nice book by Domingos kind of captures these different veins of machine learning, not just neural networks, but Bayesian, formal logic, and so on. And I've added reinforcement learning into his diagram. That would be the subject of another lecture. And so this really points to the fact that machine learning is a diverse toolbox. Right? It's really very diverse, and it's sometimes so diverse that it's hard to get our minds around all the possibilities. And that's why I kind of recommend this book as a nice sort of take on these different threads. But for the purposes of this talk, I'm just going to restrict myself to neural networks and largely to convolutional neural networks. So this is an SP generated talk. So let's talk about the signal processing landscape. Of course, in the center of the landscape is signals. And so we could ask ourselves, well, how do we define signals? And what do we want to do with them? So generally speaking, we can make a taxonomy of signal processing like this. I want to detect the presence of some signal of interest. I want to estimate something about it. It has some frequency content. It arrived at a certain time. It has some other information in it that I'd like to uncover. I might like to classify it, and classification includes all of digital communications because we're trying to classify signals from within a finite alphabet. And then I like to manipulate signals. Right? This more or less encompasses all of signal processing. And an immediate distinction we can make with regard to before deep learning and after deep learning is what I'm going to call natural and man-made signals. So the huge success of signal processing starting from 1920s and statistics is largely built around man-made signals, communications, radar, and so on. Right? These are signals that we concoct. We design them very explicitly for specific purposes. On the other hand, we have these natural signals like speech and vision, which were very difficult to deal with in the traditional signal processing way. If you look at the history of speech or vision, image processing, progress was slow and painful. In vision, when I studied image processing in the 80s, it was all about convolutional linear filtering. And if you gave me a problem, I'd have to devise some methodology to deal with it. If you gave me a new problem, I had to go back to the beginning and start. I had very few general tools. We might also throw into our definition of signals additional side information like semantic labels and context. And in that sense, what we're considering, quote, signals, unquote, is kind of expanded in recent years. So we can go a little deeper. Manipulation traditionally was called filtering, right? Take something bad out. And then there's signal generation and signal design. From an estimation standpoint, we're talking about functions. What kind of functions can I estimate? Beyond just estimating a particular feature of a signal, I'd like to estimate some function, perhaps. And then classification, which has been traditionally dominated by feature selection. Right? I take a signal, I find some features and feed some form of generic classifier. So from a deep learning perspective, we're going to see that we have whole new classes of tools now in ways that we can represent signals and ways that we can approximate functions. And so a couple of themes of this talk are how deep learning gives us the ability to do broad new forms of approximators, and it gives us broad new ability to find representations of signals. We might put all of this under some larger umbrella of information science, perhaps, which would include things like abstractions and sensing signals and transfer of signals and so on. There is no Journal of Information Science, so I guess I'm on safe ground calling it some sort of more broad category. The little stool down in the bottom is just to remind us that science proceeds on three legs: theory, analysis, simulation, and experiment. And if you think about what you do as a researcher, how you do engineering, computer science, what you do pulls on all three of these in some way, shape, or form. So what if we now view things from a deep learning perspective? So a couple of things are going to jump out at us. One is that traditional signal processing was dominated by linear processing. And when I learned signal processing, it was all about linearization. Even if something was nonlinear, you linearize locally and solve a linear problem. Your goal was to make systems which were linear. This dominated, and in some sense continues to dominate, communications, for example. We want electronics, receivers, and transmitters to be linear. We don't like deviation from linearity. We have these very fine measures of second order, third order deviations from linearity. When the system is linear, when the sensing is linear, then the processing is greatly simplified. And that's what I learned in textbooks, and that's what I learned in practice. Nonlinear problems are hard. And deep learning is giving us a whole new suite of ways that we can attack nonlinear problems generally. So deep learning is giving us new function classes, new ways to do fusion. And I'm going to talk about all of these: new ways to do approximation, new ways to do signal representation, manipulation, and signal generation. And the other thing, of course, that we all know is that most of what's happening in deep learning is data-driven. It's not that I write down a signal model like I would do in radar communications problem and work with that. And so some things that we're struggling with now are probability and novelty. How do I bring probability and this notion of probabilistic novelty into deep learning frameworks? And along with that, how do I do performance analysis? How do I gain statistical confidence? Now, these two bottom things are, of course, striking strengths of traditional signal processing, and they're striking weaknesses in the current sort of state of deep learning signal processing. So this is perhaps the most basic equation for deep learners, and you've probably all seen some form of this. It's been around for decades, and it says this. First of all, you have some data. You have input data X and some output data Y. So you've observed this, what we're called training examples. You observe this data, and it goes through some function, and you observe the output. Now, the goal here is to estimate the transfer function, the function which is taking X as its input and giving me Y. And the problem is typically defined like this. I have some loss function, say mean square error, as a measure of error of how good is my approximation. And I'm searching over some functional family. Traditionally, we like function families like linear transformations and so on. But now the function family here is a deep neural network architecture. So we're searching over some deep neural net architecture such that it well represents this mapping in this data that I'm given. What kind of functions can I do with this? Well, I can map to features Y. I can find representations in Y. I can do filtering. I can find probabilities. And I can even find approximations for things like ordinary differential equations. So from a function approximation perspective, there's a lot of things that I'd like to approximate. And as you know, and as we'll talk about, the convolutional neural net in particular gives us a remarkable ability to approximate functions in all of these different interesting cases. There is a sort of little funny piece here that is learning traditionally was defined as the performance improves over time, whereas statistical estimation is usually defined as select parameters for the best model choice. The problem as it's defined here is really estimation, right? Because this is defined as an expectation. We assume we have large amounts of data in order to approximate that expectation through some sample averaging. But that's a fine point. So, you know, the reason that we are here is not that these architectures are new. The convolutional neural net, I think, was first published in about 1990. But what happened was that as people explored larger and larger network sizes, and as they were more and more training data available, these performance curves went up. And all of this happened. One, of course, well-known notable case of this was around ImageNet. It's a remarkable story, 14 million annotated images, and because it turned out that you needed a pretty big network and you needed a lot of training data to really see the value of these things for these really hard problems like vision. So it was the progression in digital hardware and the sheer amount of time and people willing to take the time to build these really large training sets that provided a really big breakthrough, roughly 2009, 2010. It's worth noting that, not only do we have specialized hardware, but this specialized hardware now to do things like convolutional neural nets is in your phone. And so this is just a short list of devices. All the major chip manufacturers are making these. And actually this list is now maybe a couple of years old. Apple's up to A16 or something like that. The point being that these devices are everywhere and they're going to continue to proliferate. It's interesting that most of our research is around 1 or 2 neural networks. Pretty soon, we'll have dozens and dozens available to us. Another snapshot from history, these like ImageNet error rates dropped over years through competitions, and this Street View was an interesting Google problem. You know, they wanted to take images of houses and have you recognize the numbers on the houses, and word error rates dropping down and so on. And, you know, you've all seen these examples. I like the Google one because Google put this out as a challenge, which is, I think it's pretty cool when a company can get everyone out there in the community to solve their problems for free. Did you know, by the way, that it's typical for a human listener to miss individual words at a 5% rate? Seems kind of astounding to me, but you know, all of which begs some interesting questions about how much data is enough data, what is good data, when do we know we have enough data, what error rate do we think we can achieve with this? You know, everybody's, of course, we're astounded by, quote, human performance, but you know, traditionally in signal processing, we like to know what are the performance limits. And here, it's just not so clear. The convolutional neural net is really the workhorse of neural networks. And you know, there's a few things that are remarkable about it. You know, it's basically convolutions and then memoryless nonlinearities, right? Yeah, that idea has been around a long time, but assembling it into an architecture like this was not obvious at all, and really relied on sort of bio-inspiration. It's very feasible. It's simple, really. Convolutional operations followed by simple memoryless nonlinearity. You can learn all the features and the pooling of them, so you can try all different sizes, different layers, and if you have enough computing power and enough data, then you can just try and try until you get to a really good architecture for the particular problem at hand. And it learns from naturally occurring data, right? So I don't need a model. This is a fundamentally critical point. We struggled for a long time. How do I model speech? You know, we tried to model the voice track and add in the physics and the biology and on and on. Here we just take data and approximate the transfer function. Another interesting and even remarkable thing happens is that it seems to just give you features which are then linearly separable. One of the holy grails of classification problems for decades was find me features that are easily separable, ideally linearly separable. And somehow the CNN seems to just do it for us. This is extremely remarkable. So there's issues. So what are some of the more generic issues with this kind of processing? Well, a massive model usually means massive training. Right? You don't generally get free lunch here. You're going to have millions of parameters, then you're going to need a lot of data to learn them. There are many hyperparameters, how many layers of what width and so on. And we generally don't have a theory for selecting them. You try and see. Interpreting the model is difficult. We didn't create the model. It's very abstract model. So it's hard to, if I just hand you a model, it's hard for you to say, well, this is doing that. And right, so, you know, we have to rely on additional layer of sort of experimentation to reach some level of explainability. We don't have a general framework for performance analysis and bounds. This is a major issue, right? I grew up writing signal processing papers, and the papers usually went, write the model, tell me the statistical assumptions, carry through an analysis, find an algorithm like maximum likelihood, find a bound like Cramér-Rao bound, do simulations, done with that paper. And that was great because it always put us into a realm of what is possible with this statistical framework. How well do I think I can do? And in this case of deep learners, not so obvious. There's interesting questions about robustness and outliers and what is good and bad data. We'll talk a little bit more about that later, but what is good for you is bad for me, and it's not always clear. This is generally now under study under what are called adversarial networks, and like I say, I'll talk a little bit about that later. The other thing is generally we're talking about batch learning with big data sets, right? There's no adaptive online kind of processing. There's a huge thread for decades in signal processing, online adaptive filtering, LMS, RLS, all these different variants. And those algorithms, extremely valuable, very basic, extremely valuable ways to collect data online and process, right? In many, many problems that's used and is very important. And it's not straightforward in any way to take something like a convolutional neural net and do any kind of online updating. So we could say that in my science stool, not that it's broken, I don't mean to imply that, but deep learning is dominated by experimentation and simulation. And analysis is sort of, coming along. This is, by the way, not unusual for science. A lot of science proceeds this way. We find some method or through experimentation that looks interesting, and then analysis comes along and helps us with it. There are exceptions. The most notable exception, perhaps, is Einstein's discovery of relativity in around, 1905 or so. And he wrote the theory of relativity and then the theory of general relativity. And it would be at least 20 years before any kind of experiment could be done, which would even begin to validate the theory. But that's really the kind of the exception to the rule. And there's nothing wrong with this. I don't mean to imply that something's not right or that there's some failure. That's just the way it is. So a lot of the progress from 2010 onward that was going on in these classifiers and things that I showed, why were they improving, was due to numerical methods. How do I do normalization? I drop out during training. I have what's called stride, so I downsample. I do a lot of, dealing with stochastic gradient clipping methods, momentum, which gives me a smoothing in the gradient, and so on. These are all, a lot of these fall under a general label of regularization, and they led to significant improvements. But you have to kind of, we've gone through some years of, we'll try this, try that, this gets a little better, this is worse, if I combine these two. But the good news is that, because we're simulation and experiment driven in this whole area, that there's this huge code sharing community, right? So usually when you come to a new problem, you say, well, what neural network architecture should I use? And you go see if you can find somebody else's work who's at all close to what your work is and start there, right? And that's, that's a very good sign, and that we're able to do that, GitHub and all those things. So maybe we need to find a new stool. Well, no, I just kind of like that picture. I thought it was amusing, but I don't think science has changed in the sense of analysis, simulation, experiment. So a few more comments, and then I'm going to go and talk about some of the specific aspects of what we're doing and how they relate to signal processing. There's some interesting basic questions. Are all local minima equivalent? So that, most of neural network training still uses the simple idea we learned in high school, which is you take the function you want to optimize, you take the derivative with respect to the parameter, you set it equal to 0, and you solve. Right? And here you're taking the derivative with respect to millions of parameters, but the principle is identical. The backpropagation algorithm was a wonderful way to create a numerically stable method for doing first order stochastic gradient descent. It's interesting that we're still completely dominated by first order. There's been a lot of attempts at using second order, and Hessians and all these things. I mean, this is a hugely studied field in optimization for decades. But it's interesting. But a really cool thing about CNNs generally and a lot of problems is that no matter where you start and you go to a local minima, they all seem to be good. This is extremely remarkable property. It's not at all obvious that it should be that way. It's not at all obvious how you would design a family like a neural network family to have this property. And it's just extremely remarkable. Neural nets also, they give you a point estimate, right? You ask what is the probability of it's a cat, and you get a 0.72. You don't get a distribution. You'd like to have a distribution. So estimation of probabilities, you'd really like to have a distribution on that. And there is this notion of Bayesian neural nets. The idea has been around for a little while. My understanding is that they're relatively cumbersome to use. They require a lot of extra training because you're really trying to fill out the distribution from a numerical perspective and so on, but interesting. Because of the sheer amount of numerical work that's required to train a large neural net, then naturally there's been a lot of work on how do I map this, backprop and these kind of things onto multi-computer architectures? How would I do this in a decentralized way? So there's this sort of huge body of interest around how do I do the training if I have more than my laptop. There's also this whole direction of multi-agents, ensemble learning, meaning I have multiple learners going at once and then I want to combine them. This is an area of interest of mine, especially graph neural networks. This is very interesting. So, there are all these really interesting extensions, even of this sort of convolutional neural net ideas, and subject for another talk. So one key point I want to make is, so far I've kind of focused on classic signal processing, and then we've got this whole new set of tools. So this raises a basic question: what do we do with the side information, the constraints, the models, the physics, all the stuff that we labored to get in all of our applications for the last few decades, right? I don't want to just throw away the past and be completely data-driven. That, in my mind, is grossly inefficient. I know a lot about my application, whatever that may be. How do I bring that to bear? And how do we merge what we know and then go beyond big data? So there's a fundamental question laying out there. If you give me all the data in the world and all the computing power in the world, then maybe I can create this. Yeah, but that's, we're already well into the limitations of what we can do in learning. And I have some perception vision front end for an image processor that I put onto a robot. I trained it in an environment and it works pretty good. And then I go to some new environment and it doesn't work at all. And so I'm going to have to go retrain from scratch. And so we should keep in the back of our mind that there's this, when I have side information constraints, I know something about the physics, I should be able to train with less data. Right. So I like the term beyond big data because it's mildly controversial, I guess. But okay. So for the rest of the talk, I'm going to kind of walk through these aspects, these sort of generic aspects of signal processing. Function approximation, what does robustness mean? What can we do with representations and new forms of manipulation and signal generation? The way I'm going to do this is convey sort of very basic ideas and show you examples. And I'm sure many of you are familiar with some or all of these, but we'll see. So there's a question now of the convolutional neural net is a really good function approximator. And so well, how good is it? Well, it's remarkably good. It's, and this is some interesting work by Helmut Bolschi at, he's at ETH in Switzerland. And they look at this notion of how good is a convolutional neural net, say, at approximating different functions. Now, people have studied, of course, various classes of functions for many years. And it's interesting that the typical way a signal processor would think is you give me a function class, I'd like to find a basis, a signal decomposition into a basis, which is optimal in some sense. That it's a very efficient basis that I get when I go into these different basis elements or vectors, that I get independence between them. Now, you're all familiar with these, right? When you observe a radio signal and take its Fourier transform, you're expressing this into a Fourier basis, perhaps the most generally utilized basis in all of engineering and extremely intuitive. But when you get into more exotic function classes, there are all these interesting different kinds of bases, and different forms of bases turn out to be optimal for different functional classes. And it turns out that convolutional neural nets, when faced with these different functional classes, will generally learn these optimal basis decompositions. There is something inherent here which is quite remarkable, that a CNN can learn the optimal basis decomposition for particular function families, as we know different classes of functions, quite disparately different classes. So I'll just refer you to this work, and they've looked at, I don't know how many classical different functional classes. It's just really remarkable. So what about approximation? So here's an example from communications, and if you're in communications, you're familiar with these kind of examples. I want to adapt the modulation depth and the coding, the channel coding, right? Depending on the state of the channel. So the generic problem is that I have an additive white Gaussian noise channel, and I'd like to adapt both the channel coding and the constellation depth. Now, if I have higher SNR, I can drive the constellation depth higher and get more throughput, but at the same time, my error rate is affected, and so I may need to change how much coding I do. And when I do coding, I'm taking away rate, right? So adding in the constellation depth is adding rate. Adding more error correction is taking away rate. And what is the optimal trade-off? Well, it's a nonlinear thing. Right? So the way we might think of this is the system state, that is, say, the quality of the channel, the SNR, and I run through some optimization, and I get my system setting. Right? I get my choice, some kind of trade-off between these two. But I don't want to have to keep doing that over and over and over in real time because the channel changes. But what I can do is I can train a neural network to approximate the optimizer. And right, so I have an optimization algorithm. I'm going to train the neural net to approximate the optimizer. And it turns out when you do this in problems like this, not only does it learn it pretty readily, but you don't need a whole lot of training, it turns out. The neural network will sort of interpolate between these different cases nicely for us. So you see this kind of idea showing up a lot in wireless communication. I want to train the neural net to approximate some optimizer. And notice though, this is generally a nonlinear optimization. And oh, by the way, I can mix data types. So you can look at much richer problems. This is International Telecommunications Union. They put out this machine learning challenge in 2020. You can go the web and look at all these different cases. And here's an interesting example. So they have a MIMO link is postulated for in a cellular setting. So you need some training data. Well, how do you use the training data? Well, first of all, they start with some scenarios of actual street maps, and then they consider random scenes, and then they do a wireless propagation, right? And that includes ray tracing. And then out of that, you can get a whole bunch of training examples for how you would set the parameters in this MIMO beamformer, say. With all of that data run through these, physics-based, pretty realistic simulations, then they put this data out there and they say, okay, your challenge is to take this data and train a neural network that's going to be able to find this set of parameters that's really good for this problem. But you notice the input parameters could be the street scene, right? It could be a lot of things. So the interesting point from the previous slide that you can have a mix of data types, I can mix all sorts of things that I traditionally would have a very hard time. How is the general street scene and the amount of traffic there and the time of day, because I know on Fridays, at 3:30, the streets get really clogged and et cetera, et cetera. Right, so there's the optimization here, the doors are open now to something which is much more sophisticated and uses in the way that it draws on things that we wouldn't have traditionally folded into such a problem. Another way that neural networks are really taking off in terms of their ability to approximate is dealing with physics, various forms of differential equations, for example. This goes under the general rubric of physics-informed neural nets, or PINs. I'll refer you to this professor at Brown University. He has a really nice website on this. Oops, sorry. This is pulled one of his graphics. So you've got a partial differential equation, and you're trying to find a neural network which, when given some observations, will identify the parameters of the PDE, and it may even identify the order, right? Some of the higher order terms may not be there, and so on. So this is an interesting example where I know the equations, I know the functional family, and yet it's still a pain to work with. Right? When you have nonlinear coupled differential equations, they're very hard to work with numerically, even though we can write down the equations, and there may be relatively small amounts of noise. So even in a case like that, where traditionally it's very hard to make analytical progress and it's hard to do numerical evaluation, for example, run the equation forward in time, right? Like when you do hurricane prediction and things like that. And when you add in uncertainty, it's really painful. So this is just an interesting teaser for what can go on in physics. There's a huge amount of work by people in physics now around notions like this. I'd be remiss in a deep learning talk not to mention adversarial problems, and you're all familiar with the basic idea here. I've trained a visual classifier, and then you come along and you put some white and black tape on that sign, and then my classifier says, oh, it's a yield sign. There are various ways to treat the adversarial problem, but clearly the most practical, dangerous instance is when you can actually manipulate the environment in such a way as that and fool my classifier. By the way, those pieces of tape on there are not randomly placed, right? They are very specifically placed for a very specific image classifier, which was available to the people who did the manipulation, right? But that's a really, that's a really, and when people woke up to this, they're like, oh my gosh, this is a crisis, and spawned a lot of angst and papers. So you can imagine, I'm going to make a simple closed loop system. I've got a vehicle. It's driving along in this environment. It's got a vision input. I run that through and train a neural network, and I hit the controller. I say I want to stay in the right lane as I drive along. Well, there's a couple of observations here which we should make. First of all, that classifier, like any classifier, is subject to error. The only perfect classifier is one that's used for a completely trivial problem, right? We all learn this in detection estimation. Every classifier with any probabilistic notion in it has a probability of detection and a probability of false alarm, right? The rock curve, this is often called, right? So, you wouldn't design a system like this, not without accounting for the probability of false alarm and the probability of misdetection. It's just, this is engineering common sense. So it's interesting that you can create examples like this, at least in simulation land, but you would never build a real system like that. And what do you do in practice? Well, you have to think about systems, right? So not only would I have a vision classifier that's looking to classify signs, but I might also have multiple sensing modalities, right? I know I have a map, and I know I'm approaching a intersection, and therefore I know that there might be some signage there or not. I know what the shape of the sign should be. I can rely on conventional image processing features to double check, etc. Right. So really, the problem is not necessarily with the vision classifier on the front end of the driverless car, as long as we appreciate the extent to which it is useful or not, and we're careful in how we use it, right? But this notion of the semantic context is now in broad study, for example, in robotics. So semantic classifier says, well, I look at the scene and I say, that's road, that's a building, that's a sidewalk, that's a wall, right? So I'm putting semantic labels on things in the environment, even those basic labels. And when you know that, that's a tremendous source of information that I can add into my autonomous driving. So all of these things are under, broad study. A lot of this literature is driven in the driverless car community, but of course there are all these notions, and not just imaging either, of course. Okay, so we were talking about approximation and a little bit about classification. So what about representation? So this diagram on the left is intended to show what's called the autoencoder. And this is a way to find an encoding of any arbitrary signal. So think of this as input-output device, input on the left, output on the right. And the boxes get smaller, and then what's in the middle labeled code you could think of as a single vector. And the dimension of that vector z is much less than the dimension of x or x prime. Okay. Now what you're trying to do is train this neural network, and just think of this as a layered convolutional neural network, for example. You're trying to train this neural network so that the output x prime is equal to the input x. That's actually a pretty trivial problem, as we used to joke about in college. It's an all-pass filter. When I took electromagnetics as a junior at the University of Maryland, it was considered in EE, it was considered to be a no-pass filter because it was so challenging. We had to memorize the div and the curl and cylindrical and spherical coordinates. But it would be trivial to map the input to the output directly. The issue is that we force it down into this lower dimensional representation, Z. So the notion is that I first encode X into Z, and then I decode Z back out into X prime, and I'm trying to make X equal to X prime. If I can make X equal to X prime, then somehow Z, this much lower dimensional representation, has captured all the important information about X, right? You could think of Z as a lower dimensional representation now that is in some sense holding all the information that I need to recreate X, at least in this architecture. And so we use this, one of the early successes here was you take something like an object or a chunk of, say, French, you go into the coder, and then you decode back out. But now your training is not to go back to what you started with in French, but to come out with a phrase in some other language, which is equivalent. Right? So imagine a supervised training task where I have the input is a phrase in French and the output is a phrase in English, but I'm forcing it through this lower dimensional representation. So this idea was actually at the heart of a lot of successes in language translation. So the autoencoder is trying to make the input equal to the output. And then we can think of this as a sort of cross-coding. Right? It's the same architecture. So the autoencoder is actually it's a very remarkably useful tool to find representations. And it has these interesting potentials now in going from one mapping to another, from one domain to another. So far, I've talked about representations as features, for example, classification. Right? I can train a neural network to go down to some small vector, a convolutional neural net, and from there I can plug in a classifier. I can create a representation which is a sufficient measure, like in the language translation example. That sufficient measure is compact, and then I can take it and map it into some other domain. And then there's one more thing I want to talk about, and that's manipulating. Right? So we can take those representations and manipulate. We can manipulate in that representation domain and then recreate, so to speak, or then come back out. So an interesting example, this is from a paper from 2017. You see in the lower left there, Kavita Bala is a wonderful computer scientist at Cornell, and I grabbed this from her at the time, and I'm sure that there are now many, many interesting examples like this, but I like this one in particular. So it says we go into feature space and we do a linear interpolation. So the idea here is that faces are presented to a neural network and you get a representation, and then you move that representation around. So you've got this representation vector and you linearly interpolate it in a particular direction. And in this case, you interpolate it into the younger or older direction, and then you recreate the image. I'm kind of going through this quickly, and the idea though is pretty simple. And it leads to these really fascinating results, right? So I input this, once I've trained this process, I input this image, and then I move the representation a little bit in vector space, in one case to the older direction, and another case to the younger. I didn't tell you how we got there, but we had to do some learning about which direction is older and which direction is younger. So you arrive at a new vector, and then you recreate what image would have created that representation, and you get examples like this. And these are quite amazing in that they give you very consistent results, such as this notion of attribute matching. So you can add facial hair and things like that, but the facial hair is very consistent in these examples, right? So if you think about, say we wanted to do this 10 years ago, what would you do? Well, I'd get a lot of face images and then get an artist, and they would say, okay, first I got to find the nose and the eyes and the color of the hair. Then I got to kind of have a way to automatically paint in where the beard would go, and etc. It's a complete nightmare, right? You would have no idea really how to concoct such a thing. I like the older example here. As you interpolate along and add age and recreate, glasses appear, the mouth starts to hang a little more slack. And why? All of this just comes out of the training, Okay, one more, and then we will finish. And that is generating samples now from a distribution. So the classic way we would generate samples from a distribution is you tell me you want Gaussian samples, I go to the Matlab and I generate Gaussian samples. But if I give you a whole bunch of images and ask you generate a sample from the distribution of images, you'd say, well, I have no idea how to do that. So this GAN is a way to do this. Okay, so let's think of it this way. At the top there, I have a training set of images. Below that in the green is a generator. I'm trying to teach that neural network to produce samples as if they came from the training set distribution. Okay, I don't know what the training set distribution is. I can't write it down. It's surely not Gaussian. But what I want to do is learn the distribution in a way that I can produce new samples from the distribution. And the way I do that is through a second neural network, the discriminator. And I do a combined training of the discriminator and the generator in a way that the discriminator is saying, did it really come from that distribution or not? And once the discriminator gets to the point where it thinks that the samples coming out of the generator are matching the distribution of the training set, then I'm done. Now this is, hard from a numerical perspective, but now I'm using two neural nets. It's very interesting. It's got all kinds of different applications. But I think this interpretation, you're trying to generate samples from a distribution, kind of conveys the most fundamental aspect of it. And, people have a lot of time on their hands, so they like to do things like generate celebrities. You've probably seen these kind of things. The top row are entirely synthetic. And then each column, so if you pick, say, the upper left image, the synthetic celebrity, the column below that celebrity are the images which are closest in representation space to that one. And it's interesting to look at, you pick one of the ones in the top, and then you scan down and you see these actual celebrities from this celebrity database that are most closely look like that. These are kind of endlessly fascinating. When I first looked at this, I only recognized maybe a couple of the celebrities actually in all of these, which just says that I'm kind of old. But these are very, very fascinating. And of course, endless possibilities here, right? As long as you can define a set of images or a set of signals that come from some representative distribution, quote unquote, you can find new samples from that distribution. So we've covered a lot of ground about deep learning, and there are already some directions and answers to some of these basic issues. One of the, there's a lot of work now on what's called the adversarial problem. That is, what is good data, what is bad data, how is it poisoned? And I think really this whole line of work is going to tell us what is the value of information, what is good data, How much good data do you need? What is bad data? How should you sift your data before you use it for training and so on? We don't really understand that fully yet, but I think we're getting a lot of insight into this question by looking at sort of the extreme question, which is, I give you a lot of good data and I allow you to poison it. What's the worst poison you can concoct? But in general, in real life, we get all kinds of mixtures of data and we don't know how to deal with that. We're finding ways to integrate with our models physics, like approximations of constrained optimization, where I'm matching a model and learn to fit them. We can make strides in interpretation and robustness by looking at context. That is, we have to appeal to multiple forms of sensing, not just rely on a single neural network. And as we fuse with semantics and these ideas of context, we're going to build very rich systems, which build a sense of when do you trust that, what's coming out of that classifier set. There are a lot of alternatives to batch processing, online machine learning, like clustering and kernel methods. These are, decades of work in these areas, and they're also, they're also very valuable and bring us a lot of interesting tools. So the work in those areas is accelerated as well, and there's a lot of interesting things coming along in this sort of online setting. I mentioned integration with knowledge bases. That's a notion of integrating with semantic information, and there's a whole, of course, giant world of AI around semantic knowledge bases. And then the last bullet is an interesting one. We can't just jump to a design. I tell you, well, use neural networks to build something. You don't, because you're not sure how well it's going to work. What do? Well, you sort of try and build and experiment and learn and iterate. Right? In other words, you do a spiral development. And this is the world that we're in now. You have to imagine trying, retrying. Sometimes you don't even know if you're close to the solution, and all of a sudden it starts to work. So we have to give ourselves sufficient time to iterate, to fully explore the space of design. And until we get better predictive tools, that's sort of the nature of where we are, especially when it comes to systems like driverless cars. Google's solution, drive another 1,000,000 miles, right? Get more data. So that concludes my talk, and we've pulled on these major issues. We have the ability to do things in a nonlinear world that we never had since the beginning of signal processing, and the ability to fuse all sorts of different information, completely disparate information, where we'd have no notion of a joint statistical model, no clue as to how to put all that together. And so we're kind of getting these rich new things that we can do in my buckets of classic signal processing. And I'll mention one more thing, and that is, we're really building toward intelligent systems, and there are many components to intelligent systems: robotics, sensing, high performance computing, and so on. And I think one of the most interesting problems that we're all faced with is, how do we bridge the sort of classical control world, what I learned in electrical engineering, and the semantic world where we have human interaction and semantic, Google lookups and all that? How do I bridge these two? Because I really want to bring them together in one sort of umbrella of intelligence systems, and building this bridge between the sort of semantic world and what I'm calling the control world, I think, is a very interesting challenge for our time. So I'll stop there. I'm going to stop sharing. Back to you, Sammy.
Thank you very much, Brian, for this detailed talk. I mean, we have covered so much, and I think more floor for any questions. If you have a question, please just go ahead and ask your question. Okay, until you prepare your question, I have one question. I think I asked you this question last time when we met in one way or another. Do we need to learn machine learning or deep learning just to survive in the research or in the academic world? Do we have to like do research in machine learning to get noticed, if you like?
Well, it's a great question. Clearly, I think I recommend to any new student in the sciences generally to have a good basic understanding of the tools, right? Just like 10 years ago, I'd expect any student in the sciences to know what a Fourier transform was. Now I would expect any good student in the sciences, engineering, computer science, to not only know what a Fourier transform is, but also to know what is a convolutional neural net and basic ideas about it. Right? I think that's very valuable and useful. That's comment one. Another comment is that, right tool for the right job. And the more you're able to understand what's in your toolkit, the more intelligent you'll be about applying the tools. Right? So we're already perhaps crested the initial wave of look what I can do with a neural network, and now, being more intelligent about it. I get asked this question a lot, Sammy, from the following perspective. Gee, I'm a radar guy, and what do I need to do in using? Well, number one, you need to be an expert in radar to build a good radar. Number two, you need to understand what's in the toolkit, right? So you don't just throw data at the problem, and you want to be right smart about it. But certainly these tools are so good at what they do in basic things like function approximation, right? Things like that, which kind of show up everywhere, that, the short answer to your question is probably yes.
Yeah, so we have to, so this is an advice to all of the signal processing engineers and our members. Just like Brian said, you have to learn this new tool, and you have before that to have a good knowledge about your previous tool set, and then you decide what to do. But nonetheless, you have to learn or have, let's say, a good idea about machine learning. Now we have a question from
I want to
the
ask
floor.
a question. Please. I'm Salwa Ramli from
Okay.
Egypt. A little
Okay,
question.
go ahead, doctor.
Yes. Please, doctor, let's understand well, how much data do we need? How can we be confident that the amount of data is sufficient to come to conclusions? What is the measure? Is there an objective measure of the quantity of data? Thank you.
So the short answer is no. And it's very problem dependent. If you look at the history of, image processing with convolutional neural nets, it turned out that we just needed bigger networks and more data to train them. And all of a sudden it seemed that they got really good. So it really depends on context. What is it you're trying to solve, right? And you have to rely on what other people have done that might be close to you. There are rules of thumb about how much data is needed. Or in a particular application, if you could start with something which is relatively simpler version, get that to work, and then progress towards a sort of more complicated or real life case. But this is one of the challenges here. And there are problems where, people tried, and then it started to work. Why? I got a little more data. I tweaked the architecture this way. It's frustrating in some sense, but that's kind of the way it is.
Let's take the example of autonomous cars. The quantity of the data are very, very big. Can this be processed in a very short time to respond to any events that can make accidents or something like that? How are we confident in this issue?
Yeah, so you really asked a couple questions. And so one answer though is that these basic chips, the sort of convolutional neural net chips, like what's in the iPhone, are rapidly becoming a cheap commodity. The point being that soon automobiles will have them. I like to ask people, how many computers in your car? And a friend of mine said, I have 32. I said, well, how do you know it's 32? He says, I have a BMW, blah, 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 and I know it has 32 computers. Well, wherever you have 32 computers, you can imagine you'll have 32 convolutional neural nets. All of this, will naturally progress to where anytime you have computing, you'll have this available to you. So one answer is that you can do a lot in parallel and do a lot of different things, right? That takes time to progress to that. But the larger question of safety and driverless cars is subject of another talk. And, we're smack into the limits now of extreme cases in autonomy. But like I said, that's a larger question. Ola asks, what is better for building CNN, Matlab or TensorFlow Python? Matlab's a wonderful, easy to program tool, of course, but it doesn't run particularly fast. You pay that price because it's an interpreter, not a compiled. So it kind of depends on the size of your problem. And if you're learning and doing simple problems, MATLAB could be great. But once you get to where you're really engineering something, or you have to, do something which is highly compute intensive, MATLAB sort of runs out of gas, and you need to go over to something like Python. It's so that the answer to your question is kind of the complexity question. Sometimes small neural nets are very useful. Even a 2-3 layer neural net can be good at making some basic calculation for you. So sometimes MATLAB can be very good. It's also a good training tool.
Okay, Brian, if I can, let's say, use the next question by Nathan, if I pronounce his name correctly, sorry about that. He asked, is there any place for classical signal processing techniques in the future if they can be done by different neural network architecture? And my question was, it's very similar, will the signal processing change as a discipline? Let's say now we have machine learning. I think before 10 years we had the compressing sensing. Those two fields, they shook the signal processing community. So I mean, do you expect that signal processing will change as a discipline, or even the way that you are teaching signal processing in university will change?
It's certainly already changed as a discipline, right? So I think that the toolbox and the things that we have greatly expanded, but I don't think that means that you don't use classical signal processing, especially basic parametric signal processing. The question is when is this neural component or learning piece, when is that valuable and what does it add? One answer is if it's something that is very nonlinear and you can learn it, then it may be that, that neural architecture will provide you something that you couldn't readily do in a sort of classic setting. Another answer is it's very good at approximation, right? Like I mentioned, optimization. So although you can write down the optimizer you want to solve, you don't want to have to keep solving it over and over and over and over again. You can train a neural network to approximate. But you still started with a conventional sort of signal processing problem. There are other answers to that question, but I really think it's right tool for the right job. I think if things are decidedly nonlinear and you can benefit from that, the neural is good. On the other hand, you have to build neural networks that can tolerate things like slight changes in SNR and things like that. Right? So one of the issues with the neural net is to make sure that it's giving you a reasonably good answer. And part of the question there is the input to the neural net different than what you trained on? Right. So again, this is the notion of context. I have some data, I train a neural net, it works great. But if I try and apply it in a slightly different context or something's changed, I need to be aware of that because the neural network might start giving me really bad answers. So, I mean, I don't think it's an either or question.
Okay. Yeah, anybody else has a question? Please go ahead.
So Ola's got a question there in the chat.
Yes. So it's about medical imaging using CNN. Do you have any background on that, Ryan?
You know, I'm not an expert in medical images, but you know, generally you have these issues with, there are a bunch of issues that are interesting, right? Like, do you have sufficient training, right? And this is typically we'd like to have supervised training, right? Now, an interesting thing has happened in some cases because you're looking at X-rays or breast imaging and you're trying to detect the presence of cancer. Well, who builds the supervised training data? Humans, right? Humans take the images, the breast images, the X-rays, and say this is cancer or this isn't. So the best you can do then is create a neural network which is as good as a good human. Right. Well, maybe that's not a good idea. Right? Maybe you can do a lot better than that. So that's an issue, right? What is ground truth? How do you know when you're right or not in the medical problem? This is an interesting question, right? So this requires some, training, retraining, exploring. Another question is, do you have something like a physics-based simulator that you could learn from? Say an fMRI problem, right? If you have a really good physics-based simulator that you believe will give you images that you could train with, then you could produce many different images, and you can manipulate those images in a way that you can make very small changes, which might not be apparent to a human, but could be discernible by a machine learning algorithm. So those are a few of the questions that arise. And there's in the medical community, of course, the trust question, right? And the liability question and all these things. And how do you bring the human in the loop or not? Once the machine gets, quote, better than the human, unquote, then how can the physician or the expert even say, it's right or wrong? And we should be happy. I mean, these tools are fantastic, but we also, have to be really smart about recognizing the limitations, like in the adversarial problem. It's so funny to me, not funny, humor funny, but it is kind of ironic. I mean, this whole wave of image classifiers and dogs and cats came out and everyone was thrilled with this, naturally so. It went well beyond anything we've done traditionally. It seemed to rival what a human could do. And then lo and behold, those classifiers could make mistakes. Well, I mean, duh. Another interesting example to me is that, from like going back to training from a human, at least in the United States, there are these people who make decisions about whether you can get a loan or not. And what do they base that decision on? Your employment history, your income, your past, all these things, right? They get all of this data on you. And then some person would sit there and say yes or no on the loan. And if they're going to give you a loan, they would say you're high risk, medium risk, low risk. And if you came in the high risk category, then they'd offer you a loan at a higher percentage because you were, right? Okay. So then they take data like that and they train a neural net, right? So then now they're training a neural net to act like the human. And then what happened? Wow, there was racial bias. there was racial bias in these decisions. Well, if you were of one race versus another, you might be more likely to be, for the same package, you might be more likely to be classified as high risk. And you could test this, right, by taking the same package, only relabeling information about the person, different names, different ethnic names, male, female, racial difference. So the humans had bias in the way that they made these decisions. And it was discovered by looking at the neural net approximation of what the humans did. So what did we do? This is, of course, classic psychology. We blame the machine. Oh, the machine, right? The AI is biased. No, the AI is not biased. The AI is doing exactly what you trained it to do. It's mimicking the biased human. Okay, so I say this because, you know, the tool is interesting, right? It revealed the bias to us. And I think that that's very good. So, right? So these are the kind of things that leak in, right? Even in the medical profession, you know, you have some, and I can speak with confidence to this because of my father. He had some liver issues, and he was at Johns Hopkins in Maryland, one of the finest hospitals in the world, and they treated him with a certain technique. And then later he moved to Austin, Texas. He got very good care there, but they used a different technique. And I said to the physician, well, why? He said, well, you know, in different regions of the US, different methods are applied for the same problem. It's just, you know, that's the nature of the profession. So these questions are very fascinating, and, you know, the tools are good, all, you know, of which says we need to be careful how we apply the tools. Sorry, Sarah,
Okay,
that
I
was a
think,
long answer.
yeah, that was really good answer actually. I mean, Ola has one more question about trusted websites for data sets. Relating to the CNN, do you know about any trusted websites that have data sets?
Yeah, this is a, you know, it's a generic question, and I don't have a good answer for that. You know, it really depends on, you know, it really depends on what data you want. I mean, I would go to the literature if you can and get data that other people have used and they put on a website, right? Yeah, if you get some data that some guys at Stanford used and they've published, you can go get the same data, then at least you know what you're dealing with. But this is an open question, right? And there's a lot of work on going on the internet and trying to get data to learn, right? You're trying to get data for free to learn things, but you have to worry about pollution of that data. I don't think we fully understand these questions yet. Like I was talking about in the adversarial aspects, we don't, if I give you a big bucket of data and I say, is this good data? You know, I don't know. You know, did someone poison it? I don't know. I don't know the answer, and I don't have real good tools for deciding, you know, right? I need the taste tester for the, you know, someone to come in and say, oh, this is got a little too much salt in it. You know, we don't really have those kind of tools yet. So I'm afraid that's a kind of a general answer, but I don't think there is a good answer.
Okay, so I think we have time for one more question. Okay, so this is a long question from Anna. She says, machine learning and deep learning have already been proven its advantage on detection and classification. We know that, or we know the output results either from signal detection or classification are discrete. However, in the signal processing, the output results of estimation problems are usually continuous. I'd like to know whether ML or EL uh, uh, EL also works well. Thanks.
Well, there's a couple questions there. One is quantization, right? So if I'm approximating some probability, I could, you know, but once I get to 3, 4, 5 bits of dynamic range in the output, then it's, you know, I'm pretty much ignoring the quantization error. There is a, you know, there's a whole camp of people that believes that we should progress to analog neural networks to try and mimic biological processes to get to circuits which are going to be extremely low power. So that's another aspect of it. But there are things out there. There are devices, chips that people have made, like IBM, have invested significant dollars to try and do these kind of things. But it's still, not commercial off the shelf in any sense. But the other question there is, do I get, when I do classical estimation, I might get some error bound or some distribution, right? When I do Bayesian, I don't just get an point estimate, I get a distribution. And that's really much more valuable when you're doing estimation problems. We don't have a simple way of doing that with neural networks.
Okay, thank you, Brian. I think, in 1 minute, I think, or 2 minutes, we have one more question. I think it will be the last question. We don't want to make it hard for our guests. So we have an Abul Fadl, I think. In your opinion, what are the major differences between neural networks and Bayesian non-parametric models?
So the neural network generally gives you a point estimate, right? If you have a Bayesian model that you trust, and you can turn the crank on it, then you can carry distributions through and get distributions at the end. And that's extremely valuable, but not always easy to do with problems of high dimensionality, right? So you can do things with neural nets you can't easily do with a Bayesian non-parametric model because the dimensionality problem in Bayesian is really hard. But I would point to kernel methods, for example, which are highly nonlinear, can be Bayesian in the sense of non-parametric and can do very well on certain kinds of problems, but generally lower dimensionality.
Okay, so I think we stop the questions if you allow us guys to do that. I think we can conclude, I mean, at least for me, that we might use neural networks or CNN for nonlinear problems, but still we have the problem of telling how good is our answer, the performance measures. Still, this is an open issue. It's I think a very good area for research. If you can do it, I mean, please mention us in the paper if you write a paper about that. So we gave you the idea, right? Of course, you should mention Brian in the first place, and then the Jordan SPS in the second place. I would like to thank you, Brian, again for this very beneficial, very loaded lecture. I mean, it was really good. Opened our minds to so many research areas and questions and answers for that. I would like to thank the audience as well for coming and participating and asking the questions. Thank you again, and I hope that we will meet in a third time, Brian, and maybe a new talk, if maybe about graphical signal processing, if you like.
Well, Sammy, I'm preparing a new lecture for the Comms Society. It's called Pandemic Puppy, an exercise in reinforcement learning.
Yes,
I never thought
I sign up for this one for sure.
I never thought we'd get a dog again. My kids are grown, but we did. My dog is now 5 months old, and it's all about reinforcement learning. And it's actually led me to think more deeply about that topic. So I'm putting that together. I hope it'll be a sort of, general, what are the issues, and the communications comes into it in interesting ways. So that'll be for next time.
That's good news. Thank you, Brian. Thank you all, and good night.